We will learn two algorithms for clustering data. Which of them produced these why concave structures are a big deal, and back everything up with code. Imagine having a dataset and desiring to understand its structure. You would like to divide the objects in your dataset into groups, such that similar objects belong to one group, while different objects belong to different groups. This is a problem in data science called clustering, and the groups you are going to divide the objects into are called clusters. Let's talk about two proposed algorithmic solutions to this problem, as well as how each of them formalizes proximity between objects. We will discuss examples in 2 dimensions with Euclidean distance, as they are easier to visualize. From now on, each object we have corresponds to a point on the plane. KMeans builds off idea that distance between similar objects is small. We are going to select a bunch of points and then cluster each object we have based on its distance to the points. KMeans receives one hyperparameter, k, the number of clusters we'd like to divide our data into. The first step is to randomly pick k points, called centroids. These points represent current cluster centers, and our next step is to compute distances between every object and every centroid. Because we are working on the plane, calculating Euclidean distance between points is equivalent to finding the hypotenuse of the triangle whose tangents are equal to differences in x and y features of our two objects. Note the computational complexity of our actions. We are computing number of objects times number of clusters distances here, and distance computation time is linearly dependent on problem dimensionality, which is in our case equal to 2. After the computation, we know the distances from any given object to all the current cluster centers. We assign each point to the cluster whose centroid is the closest to the point. Look, right yellow point goes to its closest red cluster, because 1.3 is the least of its distances to centroids, and left yellow point goes to its closest green cluster. We will now assign each of the remaining objects to our clusters. What will be their shapes after each object will be assigned to a cluster? Will the clusters be convex or concave? How large will the red cluster be? Here comes a reminder to help us answer these questions. Perpendicular bisector of segment AB is the line all the points on which are equally distant to A and B. All the points to the top of the bisector depicted are closer to B, and all the points under it are closer to A. Violet line here is a perpendicular bisector to segment connecting cyan centroid and red centroid. It divides the plane into 2 regions, where cyan centroid is closer to an object than red centroid, and where red centroid is closer to an object than cyan centroid. By plotting these perpendiculars for every pair of centroids, we would dissect our plane into regions, and all the points in one region would have one current cluster center as their closest. In KMeans itself, we obviously do not draw these bisectors and calculate regions, we just compute all the distances and find the least one. This whole story about regions is here to help you understand why the clusters are formed with these exact shapes. We assigned all the points to clusters, but the pattern looks strange. I mean, our dataset consists of 3 easily distinguishable high-density regions with some outliers in between. All the points in every region are quite similar, and so they should be in one cluster, not in 2 different ones. Let's readjust our clusters. For every cluster, we will compute the mean values of its object's features, and then assign these coordinates to the cluster's centroid. The centroids moved, meaning we can reassign objects to clusters using steps 2 and 3, and get different results. But when should we stop recalculating the clusters? The answer is when centroid's movement is no longer significant, meaning KMeans converged. We once again compute distances from every point on the plane to every centroid, and once again assign every point to the cluster, whose centroid is the closest to the point. Even after one recalculation, the clusters changed considerably, and hence the centroid's position movement will be significant. We will continue iterating. Note that centroids are now much closer to their intuitive positions. Let's see how the next iterations will go. How long do you think will it take for K-means to converge? Will the resulting clusters be the same as the intuitive ones? And why? What would have happened if we picked K equals 4? And we got our final clusters. After this iteration, the centroids will no longer do significant movements. Even though our random initialization was far off from actual centroids, we got an interpretable and intuitive result. As you may infer from the way we use perpendicular bisectors, the clusters are convex. Their bodies resemble a mathematical pattern called Voronoi diagram. Voronoi diagram is built based on a set of dots selected from the plane. Around each dot, a Voronoi cell is formed from all the points in the plane, for which given dot is the closest one. And this is exactly the way our clusters were formed in K-means. We assigned each object to the cluster of its closest centroid. This means Voronoi diagram is a great visualization of cluster shapes in K-means. Remember, I asked you what would happen if we picked K equals 4. Well, the answer is here, and it highlights a serious problem with K-means. Its output is very dependent on its K hyperparameter, and we don't usually know in advance how many clusters there should be. So a K-means user should typically go through a bunch of different Ks to see which one fits best. There also is another issue to K-means. Check this data out. We have two intertwined crescents. If K equals 2, each one of the crescents should be a distinct cluster. But clusters produced by K-means are always convex, meaning output will be something like this. We need an algorithm that can deal with concave shapes. This algorithm is DBScan. Let's assume that points belong to the same cluster if they are located in the same high density area. On contrary, if area between points is low density, the points are in different clusters. And if a point does not belong to any high density area, we call it an outlier. To formalize this, we introduce epsilon neighborhood. Epsilon neighborhood of point A is the set of points, distance from which to A is no larger than epsilon, where epsilon is a positive number. Thus, we say point B is an epsilon neighborhood of point A if distance between A and B is no more than epsilon. Otherwise, if distance between A and B is more than epsilon, B is outside of A's epsilon neighborhood. Applied to a dataset, amount of objects in an object's epsilon neighborhood measures how dense the data around this object is. Welcome DBScan. Let us have the following data. The scale in the down left corner is once again necessary for computation. DBScan takes two hyperparameters, EPS, short for epsilon, and mean PTS, short for minimal points. Let's set them to 0.4 and 4 respectively. We start by marking all points such that the EPS neighborhood covers less than mean PTS points as noise. For example, the circle of radius EPS with center at the top dot covers less than 4 points. The top dot is marked as noise. Circle around rightmost dot of the lower cluster covers less than 4 points. The dot is marked as noise. But the circle around the dot here does cover 4 points. We include the point itself into its EPS neighborhood, as distance from a point to itself equals to 0 and is always less than a positive EPS. So we do not mark this point as noise. After checking each point for being noisy, we enter DBScan's main loop. While there are unmarked points, we pick a random one and create a cluster consisting only of this point. Then, for every point not marked as noise added to the new cluster, we add its EPS neighborhood to it. The initial point of our cluster is always not noisy, meaning we start by adding its EPS neighborhood to the cluster. After this, we pick an added not noisy point and add its EPS neighborhood to the cluster. And then we pick another one added non-noisy point and add all the points in its app's neighborhood to the cluster. Then we repeat the operation until we have picked all the added not noisy points. Note, although the cluster's leftmost dot's app's neighborhood covers the blue point, it is not added to the cluster, because the cluster's leftmost dot is noisy, and we do not add noisy points app's neighborhood to the cluster in DBScan. Then we finalize our cluster. After this is done, we go back to the loop of step 2. There are unmarked points left, and we pick a random one of them and start a cluster. Then we expand it just like the one before. For each non-noisy point added to the cluster, we add its app's neighborhood to it. After finalizing the second cluster, there are no unmarked points left. This means the clustering is complete, and all the blue points do not belong to any cluster. They are considered to be noise. Note, the 3 points in the right lower corner are marked as outliers, but if we picked min_pts equals 3, then each of these points would have had at least min_pts points in their app's neighborhoods, and would not have been marked as noise, and as a result they would have formed the third cluster. Also note that if we picked min_pts equals 3, the former left border of red cluster would have stopped being noisy, and consequently we would add the leftmost dot on the screen to red cluster. Let's see a visualization of DBScan at work. How will decreasing apps while leaving min_pts the same change the flow of DBScan? As you can see, it made DBScan less robust to gaps between points, and caused formation of more clusters. It is usually easy to determine if KMeans or DBScan was used by looking at given clusters. Here is a puzzle for you. On screen you see 2 different clustering solutions for the same dataset. One of these cluster groups is produced by DBScan, while another one is produced by KMeans. Try to match the groups to their origins. The clustering on the left has many clusters of different sizes, and the clusters themselves are really dense. It is safe to say that the clustering was produced by DBScan, with apps small enough that the circles could not cover large gaps between some objects. On the other hand, the clusters on the right seem to pay no attention to density of objects, and can be easily separated by lines. This is KMeans at work. We will now jump to Jupyter Notebook to observe how differently will KMeans and DBScan perform on different datasets. The main used libraries will be NumPy, SciPy for computation, and Seaborn, Matplotlib, and Pandas for visualization. The params cell is purely for the plots to look nice with my Jupyter themes. We will also ignore warnings for cleaner cell output. Our first data example consists of 3 clusters of different shapes. They are created using NumPy random normal function, which receives distribution mean, standard deviation, and shape of samples, and then generates an array of points of said shape from normal distribution of given parameters. Here we will have one circle-like cluster, one slightly stretched upward, and one diagonal. I've also made a handmade KMeans class that allows you to experience the clustering process step by step. Note that all the heavy computations of distance from points to current cluster centers are handled by SciPy spatial distance matrix function. You can play with this class, initializing it on any of the datasets further down the notebook, and even any custom datasets you code. The only reason I made a handmade KMeans is for it to have this step-by-step visualization feature. Actually, Scallion library has decent implementations of both KMeans and DBScan, and we are going to see them in action. But before that, let's create data that we will experiment on. Logic behind this bridge example is simple. We have two vertical clusters connected by a small bridge of objects. The nature of bridge is ambiguous. Maybe it is a cluster of its own, or maybe the bridge is formed by objects that have some defining attributes of both two-big cluster to some degree. Let's see how our algorithms will interpret this bridge data. Scallion implementation usage is simple. You define hyperparameters in instance constructor, call fit on the dataset, and then get your result in labels parameter of class. KMeans with small k ignores the bridge completely, splitting it in half, but with k equals 4 or 5 it distributes the bridge into a distinct cluster. Which hyperparameters will enable DBScan to distribute the bridge to a distinct cluster? Should we pick small apps and large min-PTS, or large apps and small min-PTS, or something in between? The answer is none of the above. Let's assume DBScan made the bridge a distinct cluster. Density of points in the bridge is far smaller than that in two clusters. So if DBScan found at least min-PTS points in app's neighborhood of most of the bridge points, it will definitely find enough points in app's neighborhood of bridge border points, and subsequently the points from two big clusters. This means DBScan will stop forming its bridge cluster only after adding the two high-density clusters to it. In practice, most DBScan can produce on this task is a large cluster connecting two cluster centers and bridge, putting periphery points in small non-significant clusters, or marking them as noise. The next example shows subtleties in Scallion DBScan implementation, namely the fact that it considers the point itself to lay in its app's neighborhood. Let's call DBScan on this data and reverse engineer its work. Apps equals 1.5 means that from each point we can reach only its neighbors by one move along an axis or a diagonal. That's how we determine that the center point has four neighbors: -1, 0, 0, -1, 1, 0, and 0, 1. Each of these points also has four neighbors. As example, 1, 0 has 0, -1, 0, 0, 0, 1, and 2, 0. The other points, however, have less neighbors. 2, 0 has 2, 1, 0 and 3, 0, and 3, 0 has only 1, 2, 0. The fact that DBScan started working means that we have at least one point which has at least 5 points in its 1.5 neighborhood, but the largest amount of reachable neighbors is 4, meaning Scallion DBScan counts the point itself when determining app's neighborhood population. There are 5 possible starting points, all with 5 points in app's neighborhood: 0, 0, -1, 0, 0, -1, 1, 0, 0, 1. DBScan started at one of these points, then extended the only cluster by all the points reachable from them, finalized the cluster and ended its work, as there were only the periphery points left. There is also a question of outlier robustness. The dataset is now the same as the first one explored, except we have two outliers far to the left. And KMeans is really tempted to assign the outliers to their own cluster, because they move corresponding centroids strongly to the left. You can see with k equals 3 we get not the result we would want. DBScan, on the other hand, is great at outlier handling. It just marks the outliers as noise and proceeds to cluster like before. We have one section left, and here we will compare DBScan and KMeans work on different structured datasets. The first one is a large normally distributed dataset. A real-world example of such data would be a map of bus stops in a large city. There are more of them in the center, yet they cover most of urban area. The second one is n independently generated normally distributed clusters. They represent a case when the data is well structured and you have to make use of this built-in structure. The third one is two moon crests, like ones from the slide before I introduced you to DBScan. Try to guess which algorithm will perform better at each of these datasets. As for huge dataset, KMeans will break it into parts of similar size. It can be useful if we interpret points as bus stops in a city, then we get them divided into groups based on location. This makes sense, as the stops are probably different in distant parts of city. The downside is points along cluster borders, while being similar, get assigned to different clusters. DBScan, on the other hand, treats the data as having one major cluster and lots of noise and insignificant ones. The reason is density. It monotonically fades as distance from center increases. Within Gaussians, the only problem both algorithms are facing are overlapping Gaussians. KMeans with too small k prefers splitting overlapping Gaussians in parts to differentiating non-overlapping but closely located Gaussians. With medium case, it treats all the non-overlapping Gaussians fine, yet cuts the overlapping ones quite arbitrarily. With large case, KMeans proceeds to cut the data even more, dividing even standalone Gaussians into parts. DBScan is less diverse. If its hyperparameters allow it to put standalone Gaussians into one distinct cluster and maybe a little bit of noise, then it will treat all the Gaussians that are overlapping with each other as one cluster. Finally, we are able to closely examine the moon crests. KMeans does clustering based solely on distance. In fact, you can see the dividing line between blue and orange clusters. DBScan is able to put each of the crests in their own cluster, because it pays attention to object density. Here is a catch. DBScan literally means density-based spatial clustering of applications with noise. This concludes the story. Remember that every clustering algorithm is based on an assumption about data structure, and pick your hyperparameters well.